And so today my goal is to give you a little bit of background introduction to plasmonics of nanoparticles and nanostructures, and then guide you through a number of different specific examples. So I know that you have very different backgrounds in material science, all kinds of other different engineering specializations, as well as bio and medical and so on. So I'll try to give some examples of each different types of applications of plasmonics. Also in my talk, I'll try to not to have much overlap with the lecture that you just had, because you learned about SERS, surface enhanced Raman scattering, and this is one of those beautiful effects that's enabled by plasmonics, right? So just keep in mind this, but in my lecture, we'll focus on fundamentals and other kinds of examples. So we'll start with introduction. When we have tiny metal nanoparticles, like gold nanoparticles, that are smaller, much smaller typically than wavelengths of light, the interaction of those nanoparticles with light is very interesting, right? Because remember, in here we have oscillating electric and magnetic fields, and in the nanoparticle we have free electrons, because this is a tiny piece of metal, and this interaction leads to delocalization of electron clouds, as depicted schematically in here, right? And so this then gives rise into new types of material properties of those nanoparticles that are not present in bulk materials like gold or other types of metal. And so all of this is because of this interaction of electrons in the small nanoparticles when they are much smaller than wavelengths of light with the electromagnetic wave of light. And so plasmonics in general is a field in science and technology where we are interested in fundamental understanding of these types of interactions, and also practical uses of plasmonics in different types of technologies. So you all know how a bulk piece of metal like gold looks like, right? So this is to remind you here. But if you would look at dispersions of colloidal metal nanoparticles in some solvents like water or organic solvents, they would look quite a bit different. And the appearance, moreover, would be also different depending on the size and shape of those particles, right? So as you would go here from the left to right, you actually have gold nanospheres, short gold nanorods, then medium-sized gold nanorods, and long nanorods, right? So although we have the same type of material in all of those colloidal nanoparticle dispersions, the appearance is very different. And it's very different also from the bulk pieces of gold, right? So as you already understand, it all comes because of this interesting interaction of the electron cloud and tiny metal nanoparticles with the electromagnetic wave. Now, it turns out that although understanding of the physics and fundamentals behind this kind of colorful appearance of nanoparticles is not that old, it's fairly recent, turns out that already long ago people found how to use it in applications like those stained glass windows, and another example in here is this cup that again has very different appearance in transmitted and reflected light, precisely because of those effects. And in all of those examples I show you in here, we have again tiny nanoparticles that are suspended in the glass, right? So the technologies, as you could see, were developed even before understanding of how they work was possible. But in my talk later today, I'll show you many examples, modern examples of applications of plasmonics, right? So before we do that, very briefly, and taking into account that you all have very different backgrounds. Some of you are biomedical, some of you have, maybe solid foundations in physics. So I'll just give you very brief introduction into the phenomena that we deal with, right? So this type of interaction that leads to the interesting effects we just discussed can be described analytically, and one way to do it is using the so-called Rayleigh approximation. Again, this is for the cases when the size of particles is much, much smaller than the wavelengths of light. In that case, we can describe the scattering and absorption cross-section, or overall total extinction cross-section, due to interaction of such particles with the light, right? This interaction will depend on the wavelengths, on the properties of the nanoparticles we deal with, as well as the electric constant of the medium in which they are suspended, right? And this is important because, as we'll see in a little bit, we'll be able to use those dependencies in different types of applications that could be developed. Now, for spherical particles, we can also describe and understand the interaction of nanoparticles with light also for bigger particles analytically, but this is mostly only for spherical particles, right? And so in here you see predictions of so-called Mie theory for both scattering and absorption of light due to such nanoparticles, which would be 80 nanometers in size in here. And you can see that agreement between predictions and experiments is fairly good. Now, in most cases, however, you will work with something more complicated than the simple cases we can discuss in here. For example, maybe you'll have non-spherical particles, platelets or rods, and then it's very useful to adopt numerical modeling techniques, which again describe those different kinds of interactions of nanoparticles, the electron cloud in nanoparticles with the electromagnetic wave of light. And so in here there is a survey of different types of approaches that you could adopt. And again, I will not go into details into all of them, right? All of them are somewhat different, but in the end, all you are looking at is at this interaction of light with nanoparticles, where you want to see what kind of scattering or absorption or extinction you get. Now, I know that later in this course, you will be introduced in much more details into one of those approaches, which is discrete dipole approximation approach. In this approach, we present nanoparticles as a cubic array of polarizable dipoles. What this allows us to do is, rather than dealing only with spherical objects, like in Mie theory, for example, in here we can describe any shapes, and that's quite a bit of interest, as you will see later from my talk. Now, another very powerful approach is called FDTD. It's finite difference time domain method. In here, you essentially solve the Maxwell equations and get similar types of results as before. I believe this approach will not be discussed that much in detail, so again, I'll not bother you with too many technical details, considering that you all have somewhat different backgrounds. But as I already mentioned, you will have hands-on experience and practice with applying this type of approach, DDA approach, in modeling the interaction of non-spherical nanoparticles with electromagnetic waves. All right, so now I would like to discuss with you how the size, the shape, and surrounding environment of those nanoparticles matter in defining the plasmonic nanoparticle properties. All right, so let's first consider size. So as you would look at small particles, only 10 nanometers or so in size, you would realize that this surface plasmon resonance peak that results from the interaction of electron cloud with the electromagnetic wave, would mostly result in strong absorption, right? So there's a lot of absorption. There would be very little scattering in this case. And so the overall extinction is mostly due to absorption of those particles. However, as you would increase size, going to 50 nanometer spheres, you would see that absorption still contributes significantly, but also scattering becomes more important as well, right? Now, as you would go even further to 100 nanometers particles, you see that now you have more scattering than absorption, right? And so this is, again, important. You can see that size matters. And as we will deal with anisotropic and shaped particles, you can then realize that you could have a combination of those sizes. Say if you would have nanorods in one dimension, the size could be, say, comparable to those smallest particles in here. In another dimension, it could be 100 nanometers or so, right? This size dependence is important when you want to design or engineer some types of behavior or response in your applications. Now, the easiest way to observe plasmonic nanoparticles and observe this kind of size dependence that we just discussed is to look at them in dark field microscopy mode. In dark field microscopy, we have illuminations through the so-called dark field condenser. What this means is if you have a source of light somewhere in here, you then also have a block of light that prevents from the direct light from coming into the sample that you study, right? So that with your objective in a microscope, you will not be able to see this direct light. And only if in your sample you have some objects that are scattering light, you will then be able to see light from those objects, right? And so this is precisely the geometry of the observation of those nanoparticles that you can see in here, right? The dark background is where you have some dispersing medium, a solvent of some kind, and those bright scattering objects are all nanoparticles of different size, right? And the color appearance and the brightness all depend on what precisely type of nanoparticle you have. And again, this type of observation is possible for very tiny particles, even if they are much smaller than wavelengths of light, 10 nanometers or so. Still, you can have a little bit of scattering from them that you can then detect in this geometry on the black, dark background of this type of observation. And again, in here you can see how what we just discussed in terms of the scattering cross-section being dependent on different parameters, including the size of particles, matters, right? Because this is a direct way of seeing this in dark field microscopy. Now, the surrounding medium also is affecting the SPR, or surface plasmon resonance, that you have. And so if you would have nanoparticles and disperse them in different types of media with different refractive indices, you could then see that this peak, the absorption maximum wavelengths, will shift depending on the refractive index of medium. And so you can see in here that as you would go from air to some high refractive index media like oil, which could have refractive index of the order of 5, this maximum wavelength peak will shift quite significantly. It's easily detectable if you have such means as spectroscopy, right? So what this means is you can use those nanoparticles to detect what is the surrounding medium around them, right? Whether you are in water or in some kind of oil, inside of a cell, or in a different environment, right? So now you remember from this my slide that I showed you already before, the colors that we had also depended on the shape of the particles, right? Because the size could stay roughly the same, but as we, say lateral size, but as we would go from short rods to longer rods, the color changes, right? So this means there should be some interesting behavior arising as we go from spherical particles to non-spherical objects. And so the simplest example is, of course, that of nanorods. So in the case of gold nanorods, we have not just one surface plasmon resonance mode, as for spheres, but two of them. And one of them is transverse, it's polarized perpendicular to the long axis of the rod. The other one is longitudinal. And they are separated spectrally from each other. So if you were to take such a dispersion of nanoparticles in a solvent, you could measure the spectrum, and you would see different distinct peaks corresponding to longitudinal and transverse modes. Now, what's very interesting is also that they are polarized, as I already mentioned, for individual particles, but if you will now take a polarizer and look at those dispersions in isotropic solvent through a polarizing film, you will see no difference in color for the reason that the dispersion itself is isotropic in nature, right? Although individual nanoparticles have those interesting polarization-dependent properties, the dispersion does not. And we will see a little bit later interesting types of dispersions in liquid crystals where this would not be the case, where we can have polarization-dependent properties as well. Now, I just want to show you a couple more examples of how we can control the shapes of nanoparticles, such as gold and silver and so on, right? So as we control the shape, also the surface plasmon resonant properties change. And this means by engineering the shape, we can control and engineer those properties. Now, a couple important properties of localized surface plasmon resonance that I want to mention to you, right? We have seen already there is strong spectral response. We have seen strong enhanced absorption due to those particles. We will discuss a little bit later the photothermal heat generation using plasmonic nanoparticles, and you will see how we can very efficiently convert light into heat, provided that this is what we need, right? Also, scattering is highly enhanced, and the electric field distribution around those particles is also well defined, right? And so in here you can see what happens with electric field around just because of this delocalization of electron clouds, right? So if you separate charges, you then have the field line distributions that are dependent on the types of particles that you have as well, for example, as you go from spheres to triangular prisms. And also directionality in the response. So engineers can produce really a lot of different variations of metal nanoparticles. And it all can be done by means of wet chemistry synthesis, right? What this means is you don't need to have fancy tools to nanofabricate complex shapes, although this is possible as well. But you could just simply use solvent-based chemistry to produce shapes as complicated as the ones you can see in here, right? And so those examples in here are all based on gold and silver chemistry. What this means is you get those kind of interesting, useful nanoparticles just by adding different ingredients to solvents, and in the end, you can mass produce such particles, which is important if you think about applications. Now, all of them can be then probed using different kinds of microscopy. So we already know about dark field microscopy, right? So when you have anisotropic particles like bigger rods, and you study the scattering from those, you would see that there is some dependence of the amount of scattering you have on polarization of light. And this allows you to clarify whether you have anisotropic particles or not. You could also do nonlinear optical microscopy, and I'll not go into details into how that works, but when the particles are small and you want to know whether the SPR properties are polarization dependent, you can use polarized femtosecond light to probe the angular dependence of the light you get upon such excitation from those nanoparticles. Now, how do you do this kind of synthesis, right? So an example in here shows how we can produce nanoparticles with quite elaborate shapes using gold and silver chemistry, right? So first, one could start from silver nanoprisms that you can see in here, and those can be obtained with different lateral sizes, so that the color appearance in a solvent will be also different. And here you can see examples, right? Different beautiful colors, right? And it's all the same material, right? But then as you would be adding gold, this gold wants to cover the edge sides of the prisms, and by controlling this process very precisely, you can get nanoframes, like you see the ones in here, right? And you can also get nanoboxes, right? Very elaborate shapes, right? And they all can be useful, if you also find ways of covering the surface of those particles with different ligands that are biocompatible. You can use them, for example, for biodetection. And just because you can design those shapes and composition of them to be, to be what you need for your particular application, the opportunities are really great, I think. Now, if you have spherical particles, right, and you would now look at the localized electric field around it, this is what you would see. So you can see the nanoparticle acts like an antenna of some kind, right? It's really enhancing the field distribution around it. And so if you have a spherical particle, this is the distribution that you would get. But if you then bring two nanoparticles, you would get something somewhat different, right? You see that the strongest enhancement would be here, right in between them, right? And so if you would now take spectra corresponding to individual nanoparticles, say we have this one in here for spherical object. But if you now have a dimer or many such dimers, you see that the spectrum changes quite a bit, and you now have not only this one peak at a shorter wavelength, but a completely new one developing at a longer wavelength and being stronger than the other one. Now, as we already saw, the shape matters a lot in defining those surface plasma resonance properties, and you can again combine both shape dependence and this dependence on how individual particles interact with each other to define those different plasmonic enhancement fields. And you can see that you can have very strong enhancement, right? When you, for example, use the nanoparticles with rough edges as the ones you can see in here, right? Those are all obtained using wet chemistry synthesis, and the rough edges help us to have the strongest possible localized enhancement, right? Because this is where you will have those fields strongly enhanced. Now you can see from these two examples of computer simulated field distribution around those particles that it's polarization dependent also, right? So this is for the polarization in this direction, and this one is in this direction. So this is also useful information, because knowing this, again, you can utilize it in different types of applications, because now the response will also depend on polarization of light that you use. Now, those were examples of how the SPR properties depend on different factors: the shape, the environment, and interaction of different particles with each other. What I want to do next is to show you one specific type of application of those dependencies. And so for this example, I'll describe how we can obtain bulk materials with orientational ordering of nanoparticles, and how we can switch those materials, switching also the optical response. So you all might know about liquid crystals a little bit, because I'm sure everybody has them in pockets, right? You use them to display information in iPhone displays, for example, in your computer screens. They are everywhere, right? The projector over there is likely liquid crystal micro display that helps us to display this information on the screen, right? So highly practically useful. What they are those interesting materials that stand in between isotropic fluids and solid crystals. They combine properties of both, because they have anisotropic properties like crystals do, but at the same time, they can also flow like liquids do, right? So if you were to have it in a cup, right, you could pour it just like water. What we have in there is some anisotropic molecules that are rod-like and orient spontaneously along a specific direction, which we call director. Now, when you have such liquid crystals and you disperse metal nanoparticles inside of such medium, the nanoparticles spontaneously order as well, right? And so the first example of this being the case, I would like to show you in here. So what we have is essentially a liquid crystal that's produced by micelles of surfactant molecules, right? So as the nanoparticles are synthesized, we typically have them covered by molecules like CTAP. Those are surfactants that have long hydrocarbon tails and also ionic groups, right, that then provide stabilization in dispersing media like water. Now, it turns out that the very same surfactant molecule, CTAP, can also form liquid crystals, right? They form those kind of cylindrical micelles. The cylindrical micelles spontaneously order in the same direction, and then they can organize the rod-like gold nanoparticles so that they all spontaneously orient in the same direction. And now, if you would observe such a dispersion through a polarizing film, you would see the color change, right? Because not only individual nanoparticles now have those polarization-dependent properties, the rod-like nanoparticles we discussed before, but the entire medium is inheriting those properties of individual nanoparticles. And so you can see the spectra with transverse and longitudinal surface plasma resonance peak that change as you are changing the polarization of light that you use. Now, we can also disperse those gold nanoparticles, rod-like nanoparticles, in liquid crystal very similar to what you use in your displays, the so-called thermotropic liquid crystal, right? So we all utilize those types of liquid crystals in displaying information. And the particles can be oriented along the liquid crystal director. Now, if you will observe this transmission of light through the liquid crystal using a polarizing film, you see very strong dependence, right? You here rotate polarizer, it goes from green to red, right? And that can be very useful. Moreover, you can design nanoparticles to be short, like the one you can see in here, 20 by 50 nanometers. Then they have transverse peak at, say, 530 nanometers for gold, and longitudinal invisible, say, at 700 nanometers, right? And then you have this kind of color change as you change polarization. But you can also design them to be much longer, like the ones you can see in here, so that this longitudinal transverse peak, longitudinal surface plasma resonance peak will be in the infrared. And this can be then useful for all kinds of applications, you know, like smart windows that we'll discuss a little bit later. So this is something that you cannot achieve with dyes, for example, because you know, the organic molecules would not have much absorption in the near infrared. Now, just like you can switch the liquid crystal in iPhone display, for example, you applying 1 volt or so. In here, we can switch this liquid crystal with nanoparticles, and as we do, we again can see the color change, right? So it will go from green to red as you apply only 1 volt or so, and you can make it a continuous process, right? So you can have this color change being very continuous. Now imagine you can have a window that will change color, go from transparent to colorful, to maybe, if you design it that way, also changing the transparency in infrared, right? It can be useful for renewable energy, privacy, and all kinds of other applications, right? Now, how fast we can switch? It's important to realize that we can do it very fast in milliseconds, and this response time, how fast all the rods reorient, is dependent on the voltage you apply, and you can achieve something on the order of a couple milliseconds at relatively high applied voltages, 10 volt or so, right? And again, you can design the glass cells of this kind to be of different thickness, and that also controls the response time, right? But you can see that the on time and off time can be fairly fast as we design, you know, such materials and devices for particular applications. Right? This is how the surface plasma resonance changes as we apply voltage, right? We rotate the particles, and because of the dependence of the SPR on orientation of those nanoparticles, we see the spectra change. right? So those dependencies can be well described theoretically, but I will not go into those details. Now, we can also orient the particles to be orthogonal to liquid crystal director, and so they will all orient as depicted in here, pointing, rod-like particles pointing perpendicular to this director orientation, which we again can switch, and again by designing the nanoparticles of different lengths and diameters, we can then control their properties by changing polarization and applying voltage. And you can see from the example depicted in here that the color change can be fairly dramatic, right? So in your display, you have red, green, blue subpixels that then, allow you to combine them, the signals in different proportions and display different colors, right? This is how we display all kinds of colors in displays. So that's why now it's important to be able to tune that color, because maybe one day we will use plasmonics to display information as well. Right? And so what's unique, however, is that we can also do it in the infrared part of spectrum, and that's where also many opportunities are. Because even in biomedical applications where this near-infrared window, transparency window of the optical spectrum is very important. We need abilities of controlling light polarization and transmission, and this is now possible using those kind of applications of plasmonic nanoparticles. So beyond nanorods, we can also utilize all kinds of other particles, like the nanoboxes that we discussed before, right? They have the shape, the outer shape of triangular nanoprism, right, as depicted in here. And they can be all again aligned in this liquid crystal medium, and we can switch them applying couple volts or so as well. And as we do this switching, note in here, we can change the spectral response, right? And this means we can, use it then for different practical applications. The nanoprisms, again as an example, can be oriented, for example, orthogonally to liquid crystal director, and that provides different response as compared to when they are parallel to the director, and so this opens opportunities for engineering. Even the much more complex shaped particles like those nano frames in the shape of triangles can be dispersed in such a medium, and we can control their response. Right? Now, what's interesting is that you might know liquid crystal display industry worldwide is on the order of $400 billion a year, right? And this is not surprising because they are everywhere, right? In our handheld gadgets, in computer screens, in projectors, and so on. Now, what this means is that we can build on the capabilities that were developed by this industry in order to now develop new types of applications for plasmonic liquid crystals, right? And so one unique thing that we, for example, can do is to control spatial orientation patterns of nanorods by controlling liquid crystal using the so-called commanding surfaces, right? So we can have this azobenzene-containing monolayer on the surfaces of confining glass cells, which would have molecular units like the one you can see in here. And so then if you use polarized light and illuminate, through, for example, through a microscope, we project something like CU that would be on your, computer screen from PowerPoint. CU would stand for Colorado University. Then we can, control in that region how the nanorods of gold or silver would be oriented, right? And so in here you can see the examples, right? So again, everywhere around, as we observe this glass cell between cross polarizers, we have uniform alignment of gold nanorods across the sample thickness. But in those regions in here, we controlled using light from a computer PowerPoint presentation, pretty much, we controlled the alignment on the surfaces in such a way that liquid crystal will twist by 90 degrees from one substrate to the other. And what this means is that those gold nanorod particles follow that twist, and therefore we can have different surface plasmon resonance modes in those different regions. Inside in here where we have twist, and outside where we have uniform alignment, right? So this is nothing difficult, right? Because as I am projecting the PowerPoint slides to these screens in the same way, I could be projecting the illumination patterns to liquid crystal and command those rods to orient differently, dynamically, right? And with light, therefore, also control the optical response of this nanostructured plasmonic medium, right? So this is very interesting because it opens a lot of engineering applications, right? You do not need to nanofabricate those kind of complicated patterns of orientation of nanoparticles. You can control them with liquid crystal, right? And so now as we design all of those types of response of dispersions of nanoparticles in liquid crystal media, we can then computer simulate using approaches like the discrete dipole approximation that we discussed, or FDTD, and predict what kind of response we should have for this ordered dispersion of nanoparticles, compare it to experiment, and you can see how good the agreement is, right? So what this means is it's not like 500 years ago we had really beautiful stained windows. We did not know how it works, but there was magic working, right? Nowadays we can use tools, the tools that you will learn during the summer school, to predict the response of those particles, right? And you can see this kind of comparison and be satisfied with fuller understanding how things work, right? So, so here I focused on one example which comes from our work in our research group at the University of Colorado. But now I want to present to you a couple other examples, some of which are from our group, some of which are also from other groups around the globe. So plasmonics is a very active field. Pretty much in every university we have people excited about this field and working in both basic science and application of those. So one example I want to show is related to optical trapping and control, right? Optical manipulation. So very simple description of how this optical trapping works. You know, we should start perhaps from a dielectric sphere, where if you were to have rays of light, you could imagine, because of refraction at the interfaces, a spherical particle like this would deflect this ray of light, right? And so what this means is that since you changed light propagation, then the light pushes us back, and as a result, we have it being pushed to the center of the beam, of the rays of light, because in that case, light just can propagate straight through without changing its propagation direction. Now, if you also have a focused laser beam, right? So here's the focal point. You will understand that the same will happen also in terms of pushing this particle into the focal point, right? Because in that case, you you will not affect the light only when it's here in the very center. And so this is very simplistic understanding of how this works, but it provides a little bit of insight into the underpinnings of optical trapping. So you can estimate what kind of forces you can exert on nano and microparticles using beams of light. Those forces would be on the order of piconewton per milliwatt of laser power, right? So this by far wouldn't be enough to, say, grab a cup of coffee, right, or some snack, and bring it to you. But it's a strong force when you apply it to tiny nanoparticles, micrometer or nanometer sized, right? Because it's much stronger, for example, 1,000 times stronger than the gravity force acting on those very same nanoparticles and microparticles. Now, again, in addition to this understanding I just provided to you, we can describe the two types of forces acting on those particles. One is the radiation pressure, right, which is pushing those particles along the light propagation direction. And the other one is the gradient force, which is pulling the particles to the point of focus of the laser beam, right, the strongest intensity point when you focus the laser beam. Those two forces are typically compete with each other, right? And when you have the gradient force winning, then you can entrap this particle, and then you can move it around. You can measure forces. You can trap many of such particles and see how they interact. Those can be all kinds of particles, bacteria, for example, or some polymer nanoparticles, or they can be also different kinds of plasmonic nanoparticles. And this is, the focus of our discussion in here, because those types of forces can be also applied to metal nanoparticles like gold and silver. And there have been quite a few works in this direction. So generally, compared to just, say, glass spheres or other dielectric spheres, the trapping of plasmonic nanoparticles is a bit more complicated, right? Because remember, we have different surface plasma resonance modes. That means the interaction of light with those kinds of nanoparticles is highly dependent on wavelengths of light that you use. But in general, you can manipulate those objects. And here I show you just a couple examples from literature where you can do. But what's interesting is that you can design the nanoparticles, and with that you design the response of those nanoparticles to laser manipulation beams, right? So I want to show you one example that's kind of unique for plasmonic nanoparticles, because doing something like this with, say, glass particles would not be easy. And so this is a geometry of the experiment. We have a laser beam, right? And we have some nanoparticles which are dispersed in a fluid medium. And as you disperse nanoparticles or colloidal particles, they are typically stabilized against aggregation, right? They are Brownian objects that undergo thermal fluctuations, very often this stabilization is provided by ligands which have some charged groups, so that the charges dissociate, and then you have like charges on nanoparticles, so that if they come very close to each other, they would repel due to screened electrostatic forces. And so this also provides the stabilization against coming to surfaces too close, because those surfaces would be charged as well, right? And there would be electrostatic screened electrostatic repulsions between the particles and the surfaces. However, with the help of the optical forces, we can overcome those repulsive forces, right? And we can print metal particles on surface. So in here I show you one example from the literature where you essentially use the laser as a gun that shoots those particles because of designed very strong scattering, right, that provides this strong radiative pressure force on the nanoparticles, and you can print them on the surface, right, into any pattern you want, because all it takes is scanning your laser beam and printing just like with regular printer pretty much, right? But just imagine how many things you can do with this, right? If you were to nanofabricate some pattern like this, it would take a lot of time and you would need capabilities for doing that, like e-beam lithography. But in here, you know, you just use laser beam and you write stuff. Now, what I want to discuss next is how those nanoparticles can behave like an equivalent of antenna, right? So we know what antenna is, right? It's essentially providing us mediation between far-field radiation and the local fields, right? And those local fields are near field, in other words. And we know how different kinds of antennas work. We typically have some kind of resonance that allows us to effectively harvest different kinds of electromagnetic waves and couple them with circuits, for example, of different devices, right? Now, what we really want to do in different applications of nanoplasmonics is to be able to couple light to the different kinds of molecules of interest for us, right? And this can be, for example, a dye molecule if we are interested in, you know, having a lot of fluorescence coming from them. Or it can be some molecule that you use in detection. Or in the example from previous speaker, this can be Raman scattering that we want to enhance, right? And for that, we again would use this kind of phenomenon. And so just like in other kinds of antenna, the nanoparticles, the plasmonic nanoparticles, provide optical plasmon resonances that are like antenna, right? And would allow us to direct these light electromagnetic waves to the proper location where we would have some kinds of molecules, like dye molecules or other kinds of molecules. Moreover, we can have very interesting effects because of this antenna-like behavior of plasmonic metal nanoparticles. And so you already saw the examples I was showing you before with gold-silver nanoparticles that had those platelet-like shapes with irregular edges, right? If we take such a platelet and also take a quantum dot in a rod nanoparticle that you can see in here, turns out that such a metal particle will have very strong effect on luminescence from quantum dots, right? And so in here you can see the observation of such metal nanoparticle in the dark field microscopy and also luminescence from a quantum dot, right? But now, if you would do time-resolved luminescence studies from such quantum rods, you would see that the decay rates are very different for nanoparticles on their own, the quantum rod, dot and rod particles on their own, and when in presence, in proximity of metal particle. So as you bring this nanorod close to this plasmonic nanoparticle, you see that your quantum rod would have much shorter lifetime, fluorescence lifetime, as compared to that far away from the particle, right? So all of those different curves that you can see in here are either quantum rod and dot in the bulk or at the surface, and then those are in here in the proximity of such metal particles, right? So you can control the decay rate of luminescence from such nanoparticles. Moreover, the quantum dots on their own would be blinking, right? So if you illuminate them and you would look at them, you would see that they are a little bit like twinkling stars, right? The luminescence from them will go on and off, and as you would measure the photon counts as a function of time, you would see this kind of trajectory, right? On and off, on and off, on and off. Now, if you bring a metal plasmonic nanoparticle close to it, you see that this behavior changes and you have mostly on then, right? So you can control how those quantum dots luminesce by simply using plasmonic harvesting effects that we just discussed. Now, another example I want to discuss with you is how we can enhance upconversion of light. In a sense, conversion of infrared light to visible. Again, this enhancement can be provided by plasmonic nanoparticles because of the antenna-like capabilities, right? So why this is interesting? Well, we all know that our solar spectrum here at the Earth's surface looks a little something like this, right? And this is just visible part of spectrum. This is where we are more or less efficient in using solar cells to convert light to electricity, for example. But there is a lot of radiation wasted, right? Now, if you could convert this to visible and then convert to electricity, our solar cells maybe could be somewhat more efficient, right? Now, this is from renewable energy application standpoint of view, may be useful, right? However, if you have biomedical background, this still can be very useful as well, because we know that here in the near infrared is where we have biological transparency window. That means light can penetrate to tissue deeply when you have this light of wavelengths in the near infrared part of spectrum. Now, this means you can send laser beams deep into tissue, right? But we know that all kinds of optical detectors like CCD cameras that we use are not very efficient in the near infrared, right? So we can have the laser beams penetrating deep into tissue, but there is no way we can detect easily the signals coming from that tissue in this part of spectrum. So if we could have nanoparticles in the tissue that could convert this infrared light to visible, we could then detect it more easily. And so this is another reason why the upconversion nanoparticles attract a lot of interest recently, right? Now, many of you might know about 2-photon, 3-photon absorption, right? Different kinds of nonlinear optical processes that you can use to achieve the same, essentially, right? But keep in mind that in that case, you typically need to have a pulsed laser, femtosecond or picosecond laser, and that means your equipment is very expensive, hundreds of thousands of dollars. That means you cannot easily afford it maybe in many medical facilities. And so if you were to use this upconversion process that we just started to discuss, you don't need pulse lasers. A regular laser will be just fine. A pointer like this could work, right? So what's the magic? How does it work? Well, the idea in here is that you would have a nanoparticle, nanocrystal lattice into which you dope different ions, like erbium, for example, right? And that allows you to design the different energy levels in the energy diagram that will look complicated like this, but don't be scared, so that the lifetime on those intermediate levels are long enough and you can absorb sequentially multiple photons, right? So although individual photons cannot breach the band gap, right, but multiple sequential absorptions allow you to accomplish that. And so what this means is then you can have infrared light absorbed, and you can still design this diagram in such a way that emission is in the visible part of spectrum, where you can see this light in the case of biomedical applications, or convert it with a solar cell in case of renewable energy applications. Now, this process is still not very efficient, right? Because of the intrinsic properties of the nanoparticles you use, and typically, you remember you would have small quantity of nanoparticles, so only a small fraction of light would be converted. You want to maximize this for all kinds of applications. And so we showed recently that it's possible to use metal nanostructures to enhance this process. And so if you, for example, attach the nanoparticles, the upconversion nanoparticles at the tip of pyramid-shaped metal nanoparticle, like gold in here, you get very strong enhancement of upconversion as well. And again, this is due to the similar effect we just discussed, the nano-antenna-like behavior of those particles. Now here's even more direct visualization how this nano-antenna effect can be useful and how it's localized. So if you fabricate such a structure with a very sharp tip in here, and then you would detect fluorescence, you would see that it's only when you come very close to this tip that you get some strong enough signal, right? As you go a little bit away, the signal drops dramatically, right? It's just because only in that case, when you're close, that you're effectively channeling the energy to the molecule from which you detect the fluorescence, right? And so what this means is that we can engineer tips of this kind, nano antennas of this kind, in order to improve our imaging capabilities, right? We all know that regular types of imaging are imaged by diffraction limited, right? So we have limits in resolution, and maybe this is one way of beating those diffraction limits. And in fact, there are a lot of research efforts in doing just that. Moreover, we can design complex shaped particles that will have a lot of such sharp tips, and this is again something obtained using wet chemistry synthesis approach, right, where you obtain very easily many of such particles that can all serve as nano antenna for different kinds of molecules, like dye molecules that we discussed in here. So in my remaining part of talk, I want to discuss with you very briefly, due to time constraints, what kind of other things you can do, right? So you can use plasmonic nanoparticles for biodetections, and the capabilities are really amazing, right? You can have very low detection limit. This allows you to detect more or less individual molecules oftentimes. And the source that you guys discussed in the previous lecture is another example, right? Now, we can also use nanoparticles to convert light to heat. And so this heat that you generate on the nanometer scale can be potentially very useful for example, killing cancer cells, right? Or you will see in a minute, you can do it, use it for actuation, where you can generate micrometer-sized muscles, for example, right? And so all you do in here is you shine light, right? And again, you design those nanoparticles in such a way that it most efficiently converts light to heat. In here, I show you how the temperature nearby nanoparticle will depend on the distance from the nanoparticle. You can see from those examples that as you shine the laser beams of light of different intensity, you heat the system locally, all right? And so this temperature drops relatively quickly. So this means you can have a way of delivering this localized heat wherever you need in biological or material system. And this is useful for so many different applications. You can use it in basic science in biophysics because you can induce transitions from, for example, gel phase to fluid phase of membranes, right, where you locally heat this membrane, and that allows you to go from this crystalline state to a fluid state where things within that membrane can easily move around. And you can probe this again using, for example, gold or silver nanoparticles, and you can study the phase transitions in different biological lipids and different kinds of membranes. So in here, I just show you an example where you can use such a particle to locally heat it, and then it explores the membrane, and you can study the phase transitions. So interesting basic science can be done, right? So you can see dramatic change of diffusion as you would heat and induce this kind of transition. Again, this is a way of inducing phase transitions locally in different kinds of biological membranes. Another example of the use of photoconversion is the case of those micromuscles, right? So you can imagine how many different practical applications something like this can have if you can actuate things with light, right? Perhaps even after incorporating such objects into biological tissue, right? So the way this works is you have a liquid crystal elastomer, right, which is like a rubber but with orientational ordering similar to that of liquid crystals we discussed, and those have coupling between ordering and the shape of those particles. So if you would microfabricate such liquid crystal rubber or elastomer rods and heat it, you will see that there is some change of shape, right? Again, it's because in this case, all molecules are pointing in the same direction, but as you go to higher temperature, they are all disordered, so this rod became a bit more fat, but shorter, right, compared to the lower temperature. Now, however, this is done by heating entire sample. If you now, however, shine a laser beam of light locally, it not only just changes its aspect ratio as before, but you can make the shape change as well, right? And so all you need to do is to shine the laser beams of light in different locations of such a rod, and you can then transform its shape. You can actuate things and apply forces and torques, right? And again, this is all because of the ability of taking the laser beam and very effectively transforming the laser light to heat in different regions of those microparticles, right? And then this results in order-disorder transition in liquid crystal elastomer and those dramatic changes in shape. Now imagine the sizes in here are on the micrometer scales, right? So, and you can actuate them with different infrared beams, which means has potential for many different applications. Couple more examples in here will show you that we can use those composite materials involving plasmonic nanoparticles as polarizers, different kinds of switchable polarizers, where you can make it a polarizer or not by simply applying voltage, and this is based on dispersions in liquid crystals that we discussed. We can have them work as color filters. We can use them in smart windows, because you can imagine how we can independently control the flow of heat and light in visible and infrared parts of spectrum. And this is precisely what we need if we want to use them in smart window applications. As you might know, the current windows that we have contribute to a huge amount of energy that's produced, right? So 20% of building energy is wasted, lost through windows. If you find ways of using plasmonics, for example, to improve efficiency, that's a huge potential for energy saving, right? And this can be done, conceptually we showed, using the dispersions of metal nanoparticles inside of liquid crystal medium, right? So this reminds you that one of the first applications that humankind developed were in glass-stained windows, right? Maybe there is a way of going beyond that achievement, now improving windows once again, making them beautiful, useful, and efficient. Now, with this, I would like to come to conclusions. I hope that in my talk, I demonstrated to you that plasmonics is really highly interdisciplinary frontier of science and technology. What it means is it provides us the means of controlling light at nanometer scales. And I demonstrated to you that we can control plasmonic properties by controlling the shape, the size, and the environment, as well as composition of the surrounding medium. We discussed the new different material designs through plasmonic nanoparticle self-assembly and control. And as well as we discussed different types of biomedical detection, therapy, and all kinds of other applications for which those particles can be useful. So I hope in some of your research in future, you will also find new uses for plasmonic nanoparticles in your research. Thank you for your attention.
Thank you.